So we were very happy to have Junho, and we'll talk about indefinitely to ternary quadratic forms.
Yeah, thank you so much. I thank the organizers for giving me a chance to speak here, and I thank the audience for being here, especially after the inclement weather conditions over the weekend. So I want to report on or discuss a joint work with Alexander Gamburd, Amit Ghosh, and Peter Sarnak that deals with some questions of the distribution of indefinite integral ternary quadratic forms with some given invariants. So on the outset, I want to introduce the notation for simplicity and call F. I want to make precise what I work with. So these are going to be primitive and integral and non-singular or non-degenerate, indefinite ternary quadratic forms. And to qualify what I mean by integral, I mean these are integral in the classical sense of Gauss. So if you write down, say, the gram matrix of this homogeneous polynomial, then the coefficients of the symmetric matrix you get are integral. And primitive means that the GCD of those entries are 1. So I might as well identify this with a subset of the 3x3 symmetric matrices. And there's a natural action of GL3Z on F by a linear change of basis, and I'll see L, the set of orbits. So there are a number of invariants we can associate to a form such as above, which I will mention. So if I have a form of the above type, then of course the determinant is one such an invariant. And what I mean by class invariant means that it's a number or a quantity associated to F that's invariant under this action of GL3Z. So EF is just the determinant of the matrix. I'll put F here, and so this is integral. And because we're working with ternary quadratic forms, we see that there's a bijection between forms of positive determinant and negative determinant by scalar multiplication by -1. So we'll assume retroactively that all these F's only range over positive determinant forms. And so if I write CLD, the set of those classes that are determinant D, then the cardinality of this set is known to be finite by classical reduction theory. But of course, the behavior of H of D as a function of D is more mysterious. Another invariant which I'll define vaguely today is rho of F, Ziegel's class invariant. Which is a suitably normalized version of the measure of the quotients of the orthogonal group of F by the unit group. And we'll use Ziegel-specific sort of normalization, which for the purpose of this talk is not too important, so I'll just leave it at this. But you may think of this as a generalization of the regulator. So the third type of invariant I want to discuss is mu of F. I'll define it in terms of another invariant, kappa of F cubed over determinant, where kappa of F is the smallest absolute value obtained by F on a non-zero integral vector. Okay. This quantity is of course more mysterious than, let's say, the determinant, but what's nice about this is it extends to a function consisting of all real indefinite quadratic forms modulo same equivalence under linear, interval linear substitutions, and also by Serre multiple. Okay, so it's a projective invariance. This leads us to the definition of the ternary Markoff spectrum. And it is precisely the set of values of this function. So the collection of mu of F. And we know by Mahler's compactness that the image of this mu from this set, say, is going to be a closed and bounded subset of the real line. And we'll order it. It has total ordering, which we'll start by denoting mu1, mu2, and so on. So on the interval between 0 and 1, you have mu1, which is 2/3, and mu2, mu3, and so on. And in fact, I can say that these first three values were determined by Markoff. The same Markoff as the one with the V usually. And I think 1904 also. And Markoff and Oppenheim made some further computations of these UI values. So to give a brief history regarding this ternary Markov spectrum, this is M is this spectrum. Of course, one can define analogs of the set for n variable quadratic forms. And in fact, in two variables, so for binary quadratic forms, this set, or more precisely, this set intersected with this half interval, was studied first by Markoff, or characterized by Markoff, based on works, and in particular, he connected the structure of this set to sort of positive integer solutions of the so-called Markoff equation. And as you can see, Markov himself further investigated the analog of this theory for the ternary forms, at least the first few values of the spectrum. Now, in 3 dimensions, our n and n4, these turn out to be discrete away from 0, and has a unique, 0 is the unique sort of accumulation point. And this follows from course, Margulis in 87 proved the opponent conjecture, which showed that the irrational forms in 3 or more variables attain values that are arbitrarily close to 0. So in particular, this mu value for an irrational form is 0. And the fact that for the rational forms, or in other words, after suitable scaling, the values of mu coming from our F, this collection of integral primitive forms, is discrete, was proved by Tassos and Smith and Dyer. On 55, conditional on the opponent conjecture which Margulis proved. Okay. And of course, for n at least 5, this set is just 0, because again, for rational forms, Margulis shows that mu values are all 0 for irrational forms, and for rational forms, Meyer's theorem tells us that an integral indefinite quadratic form in 5 or more variables attains a 0. So now let's define, in order to study this set M, let's define this function mar of x, which is the set of, well, we're going to be counting these numbers with multiplicity, so might as well count the classes. Whose mu values are bounded away from 0. So this we know by Margulis is finite for each x. And the natural question which Margulis raised is, what is the growth of this mar of x as a function of x? So numerically, Martini, actually a student of Margulis or Bruno, in 97, he computed many values of these mu i's or mu k's, and was led to the conjecture that perhaps conjecture or suggested that maybe these numbers, well, polynomial in x, in particular x squared. And in 2012, established that this is bounded above by x, the a for some large a. Something like 10 to the power of 7 or so. And this leads us to our first theorem. Everything here is joined again with the authors listed above. I'm not sure what it is. Which is that there exists some positive constant such that we have and to remark on this gamma, gamma can be given as an explicit infinite sum depending on what you mean by explicit. That in principle can be computed to some precision, which we'll not elaborate on here.
Sorry, what is this class group? Is for which discriminant? In the definition of this.
So CL is a collection of all form classes. Yes.
Okay.
Right. So note that here, when we're defining this function, we're not putting a bound on the discriminant or determinant. So a priori, we don't know that this set is finite, but it is finite because of Margulis's theorem. And any other questions or? So this is the first result. And you might say that this deals with the behavior or the distribution of anisotropic quadratic forms of indefinite type. Because as you can see in the definition of this function, the isotropic integral forms are not picked up. The mu value is always 0. So, but before going over to the statement of our second main result for distribution of isotropic quadratic forms, I want to mention some other results that come out naturally in the investigation of this type. So it is, I want to discuss following. Last number asymptotics. So namely, we defined this quantity h of b, which is a number of orbits of the primitive integral Ternary quadratic forms, indefinite forms of given determinant. And again, h of b as a function of b can be quite wild, but what we show is that on average, they follow a very nice rule. So as we order, so for b less or equal to x, the sum of these h of b's is it grows like x log x. Now the constant here, I think we're 99% sure of this, but well. And I should also mention that part of our result is that not only the average of h of d, but the average of g of d, where g of d is the number of genera of forms of determinant has the same asymptotics. So this already tells you that in the case of indefinite Ternary quadratic forms, you would expect each genus, which is defined by local conditions on the equivalence, to have only one equivalence class. So I want to make a few remarks about this particular theorem. First is that I want to mention in passing, we can, of course, ask a similar question about indefinite quadratic forms in other numbers of variables. It turns out that in the case of binary forms, so analog for binary quadratic forms in the conjecture, as far as the average of the class numbers goes, is conjecture fully is here. The expected growth is x log squared x. So this means log x squared, not log x. Now I should say that from my limited experience, usually sums of class numbers, the analytic study of class numbers, one usually encounters class numbers along with some volume term, like the regulator, or in this case, Ziegel's class invariant rho of f, which is also a type of volume. And I want to compare, therefore, this result with result of Siegel from 1944, which says that if I weigh the classes appropriately, with this type of weight, then the growth is I should mention that Siegel this was part of a much more general result concerning the growth of these weighted counts of forms given fixed signature in arbitrary imaginary variables. But in the ternary class at hand, we have this sort of reason. I should mention in passing that our method of proof of these two theorems would also allow us to establish a limit of this type, but also it is flexible enough that we have, for example, I don't know if yes, I'm numbering the theorems. So theorem 3 is now, if I only count the weight of, I take the weighted sum of these classes that are isotropic, in other words, the mu value is 0. This also has an asymptotic. Which is more complicated, but it's worth writing down. Because it is a part of local density. So part of the times here of, I'll write mu p times the normalizing factor 1 minus p to the minus 1/2. So this is the constant times the growth rate being x over square root of log x, where this mu p is the probability that a symmetric 3x3 matrix is isotropic. Okay. And by probability, I mean the inverse, the limit of the counting measure as you consider this condition of isotropy modulo p to the r as r goes to infinity. Okay. Are there questions about the statement? And I should add that maybe I'll build it here. For odd times p, we have p is 1 minus this is right. This agrees with some results of for t equal to 2, because of our choice of convention for integrality, it's a bit of a different constant, but this is my point. The reason why I mentioned this result and sort of isolated these isotropic counts is because they have an application to asymptotic growth of the numbers of isotropic forms. And here, naive maybe a rather a simple guiding question might be how many smooth Harmonic curves defined over Q. So it should be 2 of X. By height, I mean the height of the defining equation have rational points. And of course, as X goes to infinity, we want to ask for the asymptotic. So
Fixing a degree or
sorry?
fixing a degree for the.
Oh, sorry. Yeah, so I should say. What do you mean by degree? Rational points mean Q points, or rather, degree 2.
Yeah,
yes. Yeah, degree 2 rational curves. Yes. Any other questions? So, to the extent, let's consider the following. Function where we consider a compact domain, let's say in space of 3 matrices. Omega is a compact convex domain. For example, the box with this identification with the standard coordinates, and we'll define iso omega of X as a function of a real variable X to be the number of forms, integral primitive, indefinite, that lie in this box that are isotropic. So Serre in 1990 asked about the growth of this function. And using sigma test proved found the following form. And is bounded above by x06 over square root of log x. And this already shows you that as x goes to infinity, the probability that your curve has a rational point approaches 0. And just say that fully in 7 establish the lower bound on the 7 lower order. And our theorem on this growth of this function is that of course the asymptotics will have to depend on the volume of omega and how it intersects the isotropic forms. And let's see if I write for the product of the local densities here, omega tilde, say, and the same for the local densities appears here, and we have 6 over square root of log x. And here, this is locals of isotropic forms. They're isotropic over R today. So how is this related to this result? Where here on the left-hand side, we're counting with these appropriate weights the classes of bounded determinant that are isotropic, whereas here we're doing a naive count of the integral quadratic forms inside a box of increasing size, scaled size, scaled by x. Right, this is a scaling. X is a scaling factor here. On this, I will say comparatively little, but mention that there's a reduction process to our theorem 3 by using equal distribution results of this control. Which imply, and this is a relevant question for us, that if for now, let's say omega, I'll say tilde, compact region in determinant 1 hypersurface. Space of real quadratic forms. For any fixed class, the number of forms inside the class that when you scale appropriately to have determinant 1, lies inside this region is asymptotic to some localizing constant times the size of this region, a suitable measure of this region here, times discriminant, a determinant times rho. So you can see already by the equidistribution result, one can start translating this as you sum over the different classes to a count of this type, where we get the desired asymptotic from. Are there any questions or comments? And this is, of course, lowest frequency. I'm not sure that I want to erase the theorems. Maybe I will keep these two boards here.
We probably should say that the skin O uses homogeneous dynamics and graph.
Yes, right. Yes, perhaps one or two, especially to connect it with the theme of the seminar. Right. As you can see in the results of SKMO and O, and also in this Margulis theorem that kicks off this asymptotic study of this Maurer function, homogeneous. This story is intertwined with homogeneous dynamics throughout. And also Mohammadi's early results on the upper bound, explicit upper bound on the Maurer function is also rising. See. So in the remaining time, I want to give some idea of the tool, or one might say a system, that allows us to approach this question of asymptotics. And we'll discuss what we define as root packets. To explain the terminology, we define what's called packets, which are a formal finite product of local equivalence classes of forms. And root packets are packets that satisfy some high ramification property, which for the purpose of this talk, we won't define what packets are, but we'll define what root packets are and how partitioning the CL, the class of forms, according to the data of root packets, allows us to tackle these asymptotics in a pleasant manner. So let's define. Before, again, are there any questions about the theorems or their statements before I begin? So given a class of Ternary forms, we're interested in particular in the primes where C has high degree of ramification. So we'll define R of C to be the set of primes that includes 2, as prime 2 is always troublesome for us in the theory of quadratic forms, and those alt primes such that the order at P of the determinant is at least 2. And we'll define the root packet of C to be the following formal collection ranging over primes dividing primes inside this set, where this C P denotes the GL3ZP equivalence class of C. And using this division of primes into R of C and the remainder, we can write the determinant of C as R of C times S of C, where R of C is the product of the primes inside here of e to the power of that. Okay, so we've written the determinant of C as part of something which is R square free, this S here, and R of C is going to be square full in the sense that for all primes dividing R, its square divides R. For now, this up to here, this is just a formality, but the point is that if we now define temporal notation in this talk, I'll just denote by root the set of root packets. I would say observation or an idea is that the quantities such as h of d and this kappa of c, which is the infimum absolute value of the non-zero vector under the class, and so on, these are quantities that are in general quite complicated as a function of d or the class, but actually they become quite tame in this sort of asymptotic study if we fix the root packet and vary sort of the square free part. I should also write it's going to be the R or the determinant of the root packet is R of C by definition. Okay. And there are some subtle hints towards this, where, for example, if you only consider the classification of, let's say, indefinite integral quadratic forms of square free determinant, then the genus theory almost determines everything. So. Let's see, this is going to
just a multiplicacy.
What's the word? Vary and vary this. Right. So, right. What I mean is that these root packets give you a partition of CL into a disjoint union of classes, the set of classes with the same root packet. So let's see. So we're going to consider functions, let's say, because we have essentially three here, theorem 1, theorem 2, theorem 3, which by this equilibrium distribution implies this theorem above here. We'll consider the following functions labeled by these theorem numbers, defined on the root packets, so reals, where, for example, f of x1 takes a root packet and considers its ratio of the expected rate of growth with the classes measured by mar of x here, except now we're restricting it to packets with classes with root packet equal to h and so on. So x2, just one more time, similarly, is going to be over x log x. Classes such that here is going to be determinant is in this sense with condition. And also for the third theorem, but now the proof of all these theorems consists probably of 3 steps. One is to show that as functions on the root packets, these are all bounded by an integrable function, non-negative, such that f x h Step 2 is that pointwise limits or x exist, and step 3 is by calculus. So by dominated convergence, this limit is L1. And the sum of f of h is the limit of these sums. And now if you unpack this, the right-hand side is precisely the limit as x goes to infinity of, let's say, for example, 1 over x log x of mar of x. And for the second, it's going to be 1 over limit as x goes to infinity of 1 over x log x of sum of the HDs up to x. So this would give these results. And the burden is on establishing steps 1 and 2.
So when you say step 2 that the limit exists, you mean limit exists and is something explicit, right?
Explicit as in?
Well, I mean, you wrote 40, that's probably all.
Oh, right. Yes. So Yes, that's true.
depending on the rule.
Yes, and sometimes the limits are nice enough that we can write it in terms of products and so on. Yes, but for this particular problem, I don't think there's a reason to suspect that gamma has a nice description, but that's open. Any other questions? So I want to say a few words about this steps 1 and 2. For the class number asymptotics, these steps are relatively easy. So, for example, if I fix a root packet, meaning data of higher ramification, I forget where yes, this is the root packet that I fixed, where the classes are highly ramified. Then this is going to be 1 over, just to reproduce, but maybe this is very roughly something like x log x of the sum over square free s is co-prime to r of h of 2 to the omega s minus 1. So the divisor function on the square free numbers. And this sum by elementary number theory has growth equal to x log x for sum up to x, but now here the sum is up to x over r of h. So this is, very roughly speaking, 1 over r of h times x log x divided by x log x, so we get this constant here. Of course, it's not exactly r of h. There are some coprimality conditions that give us a different constant, but you notice that this r of h is a number that, such that if I have a prime dividing it, then the square divides it. So if you sum over, if you pretend that there's only a small number of h's for given r of this type, then this sum is going to converge. This gives us, in the class number setting, both steps 1 and 2. Now, for the more difficult theorem 1, the asymptotics of the Markoff function, it's really the step 1 is the hardest. And I'll mention that there are 2 ingredients that I would say go into it, where we can refine some earlier work of Watson on precisely the type of question, what is kappa of C? What is the least number represented by an indefinite quadratic form? We can show that with kappa of C is something like bounded above by radical of r of C to the quarter times the determinant C epsilon. And you already see here the role played by this higher ramification is distinct from the other places. And this is actually enough, as we note in our work, to show that mar of x is x to the 1 plus epsilon, but to get the entire result, we need sieve theory So the step two, or the second part of this step one, is to amplify this by safe theory to construct many numbers that are represented with some suitable conditions so as to get the desired result, which I guess I won't have enough time to elaborate on. Maybe I think I might have a little less than 1 minute. I want to say that theorem 3 on this weighted sum of these classes for isotropic forms can be proved in this manner. But in this setting, there's a much more pleasant observation, namely that if you define rho so E to be the sum over the C. You consider this Dirichlet series, then it has a factorization of this type some factors that are rational functions in p to the minus s and p here that allow us to get the asymptotics directly, and also in fact say more by analyzing this Euler product accordingly. Okay, I'll end here. Thank you.
Do you understand why in the conjecture related to theorem 1, the earlier conjecture, why the x squared is so wrong? I mean, but x over log x, or x times log x is your final.
My limited understanding is that perhaps the computations at the time didn't go far enough, and so maybe the expected gamma constant here is quite large. But that remains to be checked. That's the naive.
I think, yeah, this function f of h. The gamma is the sum of f of h, and that's the answer. The hardest part is to show that's convergence. That's what this dominated convergence. So that requires a whole elaborate and combinatorial argument, which, and the small h's, that f of h is rather large. And the fact that when h is r of h notation, when its value for its determinant gets large, the fact that f of h is small. Remember, you're battling the smallest number that you represented in this. That's the most tricky invariant. And then you need to put in the fact that that's small requires a lot of cancellation, like there's Burgess's bounds that go into there, character sums, and certain sub-arguments. So when h is large, somehow this f of h doesn't grow with it. But when h is small, f of h is very large numerically, and so that's why it's completely excluded. But we haven't evaluated f of h numerically yet. Once you do that, I think it'll be absolutely clear. So the small, highly ramified h's in Martini's tables, they're highly ramified, and they're creating a lot of points in the spectrum, and that's very misleading. And when h gets large, the fact that it doesn't grow is what's kind of shocking. I think we, the longest time, weren't expecting x log x. We were expecting something bigger. But this is something remarkable about the fact that ternary forms want to represent small numbers. That's really what the problem's about. Is I give you a ternary form, what's the smallest number it doesn't represent? Occasionally it can be big, but very rarely. We should work out what gamma is to a few decimal places, and if it's a few thousand, it'll be clear since he only went to.
So if you restrict to square free D, then does the constant simplify a lot, or I mean, is it the same order of magnitude and just the constant change?
Right, it is still x log x. The constant becomes smaller. I would say, right, working with square free forms is a bit like fixing one h to be a trivial h, and then so it's a particular value.
There's something that I only noticed recently in Hooley's paper. Hooley's paper is actually, for those of you who like common lens heuristics, he actually gives you a conjectured value asymptotic for sum of h of d by studying Pell's equation. Kind of remarkable. It's completely conjectural. And that conjecture that it's x times log x squared, we don't know anything. We don't know if it's x to the 3/2. Nobody's ever improved the x to the 3/2 bound, which is the trivial bound. But he does prove one theorem in that paper, which is a hidden one. But he throws it away saying it's so weak, but it's actually kind of relevant. He shows that the average of so his average in the constant there, which is the lower bound, which is not log x squared, but is the constant times x log x, where that constant shows that the average class number is not 1. So it's not true that the class number for indefinite binary forms is got 1 class per genus. He shows it's actually at least 1.1 unconditionally. Of course, he says it's going to be log. While in ternary forms, the class number wants to be small. So it's a theorem which is proved here that the average is 1 when you order by discriminant. So that's kind of that Hooley paper. Every time I look at it, it's got a little bit more there. He gives another. If you sum over primes, he reconstructs the Cohen-Lenstra conjectures, but he's actually putting something in. He's not flipping a coin. So I like the derivation there, but it's the only theorem he proves is what it just says.
Is there an analog of what Hooley does in this setting where he would predict something for this kind of count?
No, it's exactly the theorem, sum of h of d.
Yeah. But can you use Hooley's arguments or heuristics to predict this theorem?
Well, he's looking at Pell's equation,
Yeah,
and we're looking at these volumes.
Mm-hmm.
There's one thing I would say concerning this work is we've switched all the ways that, so in the Serre problem, which has been unsolved till now, everybody's trying to use sieve methods. And we use homogeneous dynamics first, and then use no sieve methods, but use this. And where in the Margulis problem, everybody was using homogeneous dynamics. We buy from Margulis that it's about integral forms, and then we use sieve methods unexpectedly to prove step 1. So we kind of switched the philosophy in both problems. First they would. And that's sort of, this interaction is very rich.
Yeah, sorry, I realized I didn't do any justice to the real meat of stage. It's a setting,
Yeah, well, let's say this, we've got a very complicated proof. We're very proud of it. And once it's simplified, it may be different. But right now, yeah, we have a rather nice, rather involved proof for that, which is kind of, seems quite subtle. And as I say, we really, at some point, really weren't expecting x log x. And Watson's ideas are quite deep. They're useful.
Any other questions?
Right, that's the